Okay, so the topic today is going to be energy in a pendulum. So we've got conservation of energy. And basically for a pendulum, that's going to take two forms. There's going to be kinetic energy and gravitational potential energy. So basically, if I just sort of think about if I've got a pendulum and it's going to be here, and then it's going to do a nice circular arc, so at some later time it's going to be here, and some later time it's going to be here, and we're going to call this A, B, and C, and it just swings back and forth like that. Well, we're going to say that at A, the kinetic energy is 0 joules, and the gravitational potential energy is going to be at a maximum. And then at B, the kinetic energy is going to be at that max value, and the gravitational potential energy is going to be 0 joules, because we're going to take this to be the bottom of the arc. And then at C, it goes back to being the kinetic energy is 0 joules, and the gravitational potential energy is at its max. And so basically, if there's no friction in the system, if there's no air resistance, if that's just a perfect pivot point, and we do this in a vacuum, which of course is unrealistic, it would just swing, it would convert gravitational energy to kinetic energy to gravitational energy to kinetic energy to gravitational energy, and that energy would just sort of slosh back and forth between those two forms forever and ever and ever. Of course, in any real system, you're going to have what's called damping, which is damping is going to be frictional forces basically that remove energy out of the system. So why don't we ask a couple of questions. I think I'll just do one example problem. I will say oh, and I forgot as I was writing that, I'm going to have to tell you the length of the pendulum. Let's call it 1.48 meters. Okay, so very quickly, what I do is I say, okay, if I've got a pendulum, and I sort of create this sort of arc like this, and I make a right triangle like this, and I know that this is 1.48 meters, and I know that this is 20 degrees, and so I know that if I use cosine, that's going to be 1.48 times cosine of 20 degrees. So it's going to be 1.39. So this here is going to be 1.39 meters, and that means that this right there, if the pendulum was just hanging straight down, this would be 1.48 meters, but now it's 1.39 meters, so the difference there is 0.9 or 0.09 meters. And so that's the height that I plug into if I say my kinetic energy at the bottom is equal to my gravitational potential energy at the top. And so I say 1/2 mv squared is equal to mgh. And some people might have said at some point in time, hey, what about the mass? I need to know the mass of whatever it was that was on the pendulum. But I don't, because my masses cancel out. And so I get v squared equals 2gh. V equals the square root of 2gh. And so I get v equals square root of 2 times 9.81 meters per second squared times my height, which is 0.09 meters. And I get my maximum speed at the bottom is square root of 2 times 9.81 times 0.09, and close that out, 1.32 meters per second. And finally, the last thing that I want to note, I could sort of go into this exhaustively and I could say, okay, well now suppose it's 1.32 meters per second at the bottom, and suppose it swings out to a maximum angle of 20 degrees. Well, what would its speed be if I was at 10 degrees? And so then I could go and I could do, well, I could figure out what the gravitational potential energy was at that point in time. And then I could figure out how much kinetic energy I have and how much potential energy I have, and I could sort of work it out. I'm not going to work it out. What I want to say is that if this is theta max, then this has to be theta max. And so one of the things about conservation of energy is however far I pull the pendulum up on this side, that's going to be the maximum energy that it has. And so when I release it, it's never going to go higher than that on the other side. So just a quick diagram, just finding a space that's available on the page. Okay, so suppose here's a pivot point and you're on a cliff, and there's a cliff over here, and so you sort of, well, let's put and so if it kind of works out that this makes a circular arc. Let's kind of just sort of approximate that. And so you go, hey, you know what I'm going to do? Is I'm going to grab hold of this vine. I'm going to grab hold of this vine and I'm going to swing from here, and then I'm going to swing and my potential energy is going to turn into kinetic energy, and I'm going to swing up to this cliff. Well, as you can probably already guess, that's just not going to work. You can swing on your vine from this cliff down to this cliff, but you cannot swing on the vine from this cliff up to this cliff, because here you're going to have kinetic energy when you drop down to the lower cliff. On here, you're going to run out of kinetic energy right about there, and then you're just going to swing back to where you came from. Okay, so that's energy in a pendulum.